cover in this video is kind of this trick for unrolling, or at least solving, these recurrence relations. So what we saw last time was that this tree was kind of lopsided, right? And our end goal is to be able to sum up all of these nodes in this tree. Right now it's kind of tough given that our tree is kind of lopsided like this. And so one trick that we're going to apply here is by noticing that we are performing big O analysis. In other words, big O represents the upper bound on the runtime. So what that means is, if I want to say that T of n is O of something. In other words, I want to find T of n is O of the sum of all of these nodes in this tree, right? I want to find what that is. If I want to know that, but let's put that aside for now. Let's say I told you that G of n is greater than or equal to T of n, and also that G of n is big O of, let's call this X. In other words, I guess put more plainly, I'm going to give you a function that is for sure greater than T of n, and then I'm going to prove the big O bound of this bigger function. Now what can we say about X, or what can we say about T? I guess I kind of just gave away the answer here. We can say that T of n is also O of X. And that stems from the fact that big O represents an upper bound. And I guess if you wanted a more clear example of this, let's just use, for example, let's say we're comparing people's heights. Right? And I said that person A is taller than person B, but person C is taller than person A. So like, what does that tell you about the relationship between person C and person B? Well, now you know that person C is bigger than person B. Right? In other words, we didn't know the upper bound for this function. But if I told you the upper bound for a bigger function, then that upper bound for that bigger function is surely an upper bound for the original function. And we're going to apply that here. Right? And so what we're going to say is we don't know how to add these nodes up, but it would sure as heck be a lot easier if we had not a lopsided tree. So what I'm going to do is going to apply this concept here and make my G of n even bigger than T of n. And we're going to bring this O of 1 down here. And we're going to do this for every single intermittent branch in the middle over here. We're going to bring all of them down to this extreme level. And now we have a symmetric tree, which will be much easier to solve for. And once we find the sum of this symmetric tree now, we know that that will be a big O bound for T. So if I were to write out this T of n in a different way and utilize these number of O of 1s, these number of O of 1s that we made here, well then I would say that T of n would be 1 times O of 1 plus 2 times O of 1 plus 4 times O of 1 plus 8 times O of 1, right, where each of these terms represents the O of 1s at a level, plus 16 times O of 1 plus dot dot dot. So one thing we can say is that we can notice that these are all powers of 2. Right? So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and lastly 2 to the 4, and that continues. The question is, when does it stop, right? Well, we went from 2 to the 0 to 2 to the 1 to 2 to the 2 to the 3 to the 4. And now given that this height is n, we know that this will stop. This will stop at 2 to the n times O of 1. And so now if I were to write this in summation form, we can say that this is the sum from I equals 0 to n of 2 to the I times O of 1, which is O of 1 times the sum from I equals 0 to n of 2 to the I. And it looks like I've run out of space, so let's just do this in the next video.